When we talk about expected return, we don't know what the actual return is going to be, so the expected return, it's basically a best guess. So a lot of, and we'll talk about it in a second, but a lot of things can happen, and we put all that information together, and we take, our best guess. And as we've talked about all semester, it's based on the risk associated with the asset. The more risk, the higher the expected return. The lower the risk, the lower the expected return. People don't like risk, and in order to accept risk, there needs to be a higher level of compensation, a higher level of reward, or at least expected reward, and that's the relationship we have. So, in order to understand this trade off between risk and reward, we need to be able to measure, we need to understand expected return and risk, expected risk, and we're going to go ahead now and cover some. We've covered some topics. We're going to move forward and talk now about expected return and expected volatility. But volatility is one way of measuring risk, and so let's learn about expected return and expected volatility. So, in practice, if we're trying to come up with expected return and expected volatility, there's two methods that get used. The first is to look at past data and assume that the past is reflective of the future. And so what people will typically do is find the mean return, that the average of past data, and say that's what we expect in the future. Find historic variance, historic standard deviation, and say given what's happened over a length of time, and in practice you want to use as long a period of time as you can, in general will tell us something about what's going to happen in the future. And we've covered this approach as far as how to compute the average and the standard deviation of the variance based on historic data. What we're going to cover right now is taking a look at what could happen in the future and making projections based on that. So we say, what do we think could happen in the future? And therefore use that information in order to compute expected return, variance, and standard deviation. So in this class, whenever we talk about expected, projected, or forecast, we're going to be using this methodology. So I mentioned this methodology, but we're not going to use that in this class to project. We can use it to measure historic returns, but in this class we're going to be looking into the future, say what could happen, and let's use that information. And let's talk now about how that actually plays out. There's three key questions that we want to ask if we're going to compute the expected return and expected volatility. First is what could happen. So what are the possible outcomes, states, or scenarios? And we like to have notation so we can make it something that we can use to quantify. So we call these outcomes S, often for states. There's 1, 2, all the way out to S. There can be any number of them. In this class, we'll tend to have relatively few. Outcomes will often be bad, medium, and good. But there's you can have a large number of possible outcomes. We'll generally just have a couple. So what could happen? Question number 2. If for each thing that could happen, what would the return be? So we've got the capital R, and then in parentheses it refers to the individual states. So R1, R2, R3 tells us what would be the return if things turn out bad. What would be the return if things turn out medium? What would be the return if things turn out good? And the last question is, what is the probability of each outcome taking place? So it's great to know that there's 3 possible outcomes, but it makes a big difference if there is a 33 and a third chance of each of those happening, or if there's a 1% chance of 1 and 2 happening, and then a 98% chance of the third. So what's the probability of each of them happening? And for here the notation's the little p for probability, and the parentheses has the S for the different outcomes. And a good check is to confirm that the sum of the probabilities equals 1 or 100%. And that basically is saying, look, we're modeling this so we know everything that could happen in the world. We know one of those things is going to happen. And so the probability of each of those happening we have, but the sum is equal to 100 because we know that one of those is going to happen. You know, we flip a coin, we know it's a 50% chance of heads, 50% chance of tails. We're not sure what's going to come up, but we do know it's going to be a head or a tail. So let's put it together. Expected return is just a weighted average of the returns in different states where the weights are the probability. So again, here, you know, you've got if state 1 comes out, happens, this would be the return, likelihood of that happening. State 2 happens, this is the return that would be experienced, the likelihood of that happening. So you can see the expected return takes into account all of the things that could happen, all the different returns we could have, and then weights them by the likelihood of those things happening. The expected variance is just a weighted average of the squared deviations. And so you figure out the expected return for across all the possibilities. Then for each state, you get your deviation. So if state 1 happens, you know, state 1 or the return in outcome 1 minus the expected return, that's your deviation. Then you square that. So that's your squared deviation. And you want to make sure that that has the weight associated with how likely it is to happen, so it gets weighted by the probability. And one important thing to recognize here is that there's no adjustment made to the weights. When we were looking at historic data, if we have n of them, they all get weighted by 1 over n minus 1. Here there's no adjustment, because the way we model it is we don't know what's going to happen, but we know everything that could happen. So we don't have to take a statistical penalty. So you weight them all, you add them up, and you get essentially a weighted average of the squared deviations, where the weights are the likelihood of these things happening. And finally, the expected standard deviation is just the square root of the expected variance. And notice the standard deviation is often denoted by sigma. The variance is often denoted by sigma squared. So very quickly, you can do this in 5 steps. Number 1, get the expected return. It's just the weighted average. And again, the weight is the probability. Step 2, get the deviation. So for each state, each possible outcome, the return that would happen minus the expected return across all states, that's your deviation. Square them. Again, we do that so that they all turn positive, and the bigger the difference, whether the return in each state is less than the expected return or greater, the bigger that magnitude, the bigger the square is going to be. The weight for the expected variance is the probability. There's no adjustment that's made because, like I said, there's no statistical penalty because we assume we know how the world works. We don't know what's going to happen, but we know how the world works. And then you put it all together, where you take a weighted average of these squared deviation terms where the weights are simply the probabilities.